All right, let's get started early. What do y'all think about that? Notice we've changed colors. It's going to be true, false. How are you going to keep them from cheating? They're sitting next to each other. Oh yeah, they have to sign the honesty statement. Yeah, next time we'll have to jumble them up. He doesn't think like that. As a Turk, he knows that if you cheat, he kills you. And by the way, he might be wrong, okay? All right, so the concept of material balance is that we have a setup, and you can think of this as oil, gas, and water. This is the initial state. Oh, we don't have green. It's got to be green, green, green. So there's gas in the oil phase, and there's water in the gas phase and water in the oil phase. And what happens is you come along and you produce something. You produce some water, hopefully you produce some oil, and you produce some gas. And what happens is things change. So now the oil zone is smaller, and the gas zone inside the oil is perhaps smaller. Connate water has expanded. And also, you have something that's a bit of a surprise. You have water that's encroached in your system, and you also have rock expansion. But the way this works is we write an equation that says that at any given state and time, we monitor, we account for this, the particular volumes that have existed, and then we subtract those which are produced from that. So that's the easiest way to explain the material balance equation. Back in the good old days, we used to have to derive this. Are you having to derive this in 323? Maybe. Maybe you'll see it on the test. Who knows? So you have to have accurate production measurements. You have to have estimates of average reservoir pressure. You know, PVT is no problem. Reservoir properties, no problem. But it's that production measurement and that estimate of average reservoir pressure that's going to get you every time. Now, back in the good old days, when they were ignorant, and we still are, this is interesting because when you read the papers from the 50s, the reservoir was so simple, and now it's so complicated. Do you think it was really simple then? No. It was just their understanding of it was simple, and now our understanding is complex, and your understanding will be more complex. My advice is always go back and look at the simplest possible scenario. But having said that, let's see what they would do back in the good old days. Okay, advance. All right, so this is ye old kidney bean field. Actually, it kind of looks like a club. This is the Schuler field, and this paper came out in 1944. Is that a long time ago? Yeah. So this is the 22nd of February, 1938. That's the pressure map that they give. And then they come back and they draw in all the new wells, which you can see all the new wells are over here. And then they calculate a pressure distribution across that reservoir. You kind of like how it does a U-turn there? Is that a good idea? Do you think pressure distributions do U-turns? Probably not. How accurate do you think this distribution of pressure is, Dilhan? Yeah, it's not very accurate. It's probably based on spot pressure measurements at the surface, but it's better than nothing. And then they come along in July of 1940. This is February of 1941, and they draw another map. These are the wells that they've tested, and the numbers are too small to read, but those are where they have pressure points. And then they come in the middle of July in 1941, and then the end of 1941, December. And you can see now you're starting to see little areas that have sort of weird shapes and that sort of thing. But this is the pressure distribution that they're calculating in this reservoir. And they're paying somebody to go out and take these measurements. And then, in the end, we come out in 1942, about a year later, and you can see that there's other pressure distributions as well, kind of a tongue here, some things going there, and so on. So if you're going to perform a material balance on this system, you have to know the cumulative volume produced for the entire field. You have to know the water, the gas, the oil rates that those volumes were produced. Then you also have to know the any water influx, any re-injection that you may have put in here. And like I said, you also have to know the pressure distribution, which Dillon, being his skeptical usual self, says that this isn't very good, but okay, we'll go with that. There's no way that we can isolate the reservoir into these cells, okay? There's no way that we can say that there's little areas that are assigned to this. So what we're going to do is we're going to average using cumulative production as a surrogate for volume. Did any of you guys buy the Dake book? D-A-K-E? Nobody did? Okay, yeah, it's in there. They talk about it in there. Okay, and then the pressure test must be representative. There must be some way to extrapolate to average reservoir pressure. And then the average pressures are averaged over an area or a volume. So we're ready to move on to the next phase of our life, which is to perform the material balance. In school, this is what we give you. This is another field, sorry for that, but this is Van Everdingen in 1953. Van Everdingen is actually most famous for a paper in well test analysis that he and another guy wrote in 1949, sort of the fathers of modern well test analysis. Let's go through this very systematically. Now, we're not going to ask them to reproduce this on a quiz, are we? That'd be kind of cool if we did, though. All right, so here's the reservoir pressure. The average reservoir pressure drops down and goes back up. A bell should go off in your head, right? The average reservoir pressure cannot go back up unless there's injection or massive water influx. Okay, let's go look at the water influx. This is not the water that influx, this is water that was produced. You guys like this old cityscape diagram? I think it's cool. You realize somebody drew this by hand? This is back in the good old days. Then it kind of peaked and dropped off. So there's the water. This is WP, produced. All right, and here is NP. This is the oil. How do you like that 90,000 barrels of oil a day, class? Would you like to have a piece of that? Yeah. NP. And then they didn't give us the gas rate, but they gave us the GOR. The GOR was flat or unknown, and then it bounced around, it went up. The water comes in, and the GOR goes down, so there's probably some pressure support, we don't know for sure. And then it drops back down, probably again, possibly some pressure support. Okay? Now, what's the most important thing on here? Well, it could be the number of wells. Here's their development sequence. This is 0, and this is 40. So it went from 0 to 40 wells pretty quick. Why did it go from 0 to 40 pretty quick, class? It was during the war. They needed the oil. So they developed this thing as fast as they could. Okay? And then the number of wells stayed constant throughout the period we're looking at, which is good because that kind of keeps us honest. All right? Now, here's the reservoir pressure. I'm going to have to start using a dash line because it mingles with the other red one. There's your P bar, we think. Okay? So we don't have GP, but we have GOR, and we can get GP from that. So we have what appears to be everything we need. Oops, GP from GP. The old man's losing his mind. Okay. But what about that pressure profile? Is it okay? Is it good enough? So if I use your quiz, as a straight edge, and say I'm going to make an approximation. And that's my approximation. Well, I kind of drew it cattywampus. But is that okay? And then how come it flattened out? How did that happen? Anybody? The author's contention is there's water drive. Is water drive going to increase to the point where it replaces enough molecules for the pressure to go up? Maybe on a local basis, yes, but on the entire reservoir, probably not. It's probably not in the time frame, not while the reservoir is still under production. You may see it arrest, from your perspective, it will slow down and decline, but it's probably not going to go back up. Any other comments about this? Sorry? Louder.
Are they choking down the production?
I think it's the water production. I think the water production got so high, they're up in the 100,000 barrels a day, that it's probably taking care of that itself. Now, what we'd like to know in a practical sense is where that's occurring. It'd be nice to have a map and see where the water production is and so on. Maybe we could go back and look at this paper and there would be some of that, but probably not. They probably weren't documenting it. I did see one example one time of a reservoir in Mexico where the wells were placed like this, and they actually watched the water come up, and these wells would water out as a function of time. But, of course, when that happens, it's too late anyway. Okay, so the big question for us is, what is WE? Water influx. Dilhan? Do you have that crystal ball thingy that we use? You can use a crystal ball. You can use a Ouija board. You can use the old King Tut thing, right? No? What's this look, man? Come on. Give me a hand here. I'm trying. Where do we get WE? It's a model. This is the hard part. If it's a model, who selects it? You do. How do you know you're right? I told you that there's something like 700 papers on water encroachment. There's at least a half a dozen water influx models I can think of, maybe a couple more for you. So we could take the room and we could assign each person their own model. And what's going to happen is you're not going to get the same answer for your interpretation. The same thing is going to be true if we're doing reservoir simulation. We're going to have to capture that. All right, now this is the oil material balance equation. Everybody take note. This is P bar, average reservoir pressure, initial reservoir pressure, 1 over oil in place times total compressibility, BO, which is body odor, BOI, which is initial body odor, and then NP. Okay? So, all things being equal, and Dilhan mentioned that on the quiz, what are your variables? P bar and NP, right? This thing is going to be a constant. We can call it MBE. How's that? You like that, Dilhan? Dilhan doesn't speak today. He's mad at me. Dilhan didn't win the paper contest. He's upset because I made him enter. I have a rule, you know, that people who win the paper contest probably, well, I better not say because we're being recorded, but, you know, people who want to win the paper contest probably sick in the head, but that's okay. Is that true, Mr. Zanero? Look, it's kind of like kissing your cousin, okay? It's a local event. I want you to do your best. Well, maybe the kissing the cousin part we'll leave out now, but, you know, you're supposed to do your best. But what I really want to see you do is go on and start writing SPE papers. Of course, that just went in one ear and out the other, right? That's okay. What's the difference between you and all those other people who write papers? You're probably more objective than they are, and you might even be a bit smarter. Okay, so we have the pressure profile coming down like this, and we're going to draw our magic line like this. Sorry, my data didn't fall exactly on a straight line. And this is NP max. What's another name for NP max? Sorry, louder. That's reserves. Now, what determines NP max? Because somebody sent me an email today and said, how do you distinguish between gas in place and gas reserves? Well, that's actually not that difficult because usually gas in place and gas reserves are pretty close. But contacted gas in place and gas reserves is two different things. But for oil, the amount of energy that you have to push the oil out in this particular formulation is small. That energy is contained where, class? In the compressibility term. Okay, it also is in the body odor term, but we're going to forget about the body odor term for right now. We'll say it's basically negligible. Okay? And for those of you who've forgotten, we're looking at this part of the formation volume factor diagram. This is PB. We're looking over here. This is BOI, and this is BO, and then there's the rest of it here. So this is what we're talking about. We're talking about this segment right here. Pressures above the bubble point. P greater than PB. Okay? So why don't we make P bar versus NP plots, Mr. Stone? Mr. Stone, who's your worst enemy in this room? Yes, thank you. Marmina, who's your worst enemy in this room? Oh, yeah, you love everybody. You're not going to tell us? Guillermo, where you at? He's not here today. What a surprise. Okay. Sorry? Who else wants to volunteer? We got to bring the roster down so we can pick on random people. Where's Mr. Broussard? So we know who you are now. Okay, you ready? How come we don't make this kind of plot? Is it because we don't know what the average reservoir pressure is? We can measure the production for all these wells, but how do we get P bar as a function of time for this system? That's going to be the trick, right? So that's impossible. And what do we say, Marmina? No P bar, no analysis, right? Okay, so we're done. But if we could do this, we could determine, because this MMBE has N in it, the oil in place, we could do that. But we can also do this and estimate NP max. We're going to talk about this some more later on in the semester when we talk about production data analysis, but there's something called a flowing material balance plot where for a single well case we can convert it into a surrogate for P bar and do some analysis. Now Dr. Momora, he's going to have you working with that equation, but he's also going to have you working with the one below it. And let's go through very quickly. This is going to be like the little game that used to be on the Saturday morning cartoons. I'm going to write in blue everything that we know. We know BO, we know the producing gas oil ratio, we know the solution gas oil ratio, we know BG, we know BW, we know BO, BOI, RSI, RS, BG, we know BOI, BG, GI, we know the number 1, we know the number 1. So I'm just seeing if you're paying attention. BOI, water saturation, initial pressure, and formation volume factor. Okay, what don't we know? We don't really know C sub F. We probably know C sub W, that's probably okay. We definitely don't know P bar. I'm sorry, it's a measurement. I should take that back, pardon me. We're going to assume we know P bar. We'll assume we know that. And therefore, we also know NP. What am I missing? Okay, so what we don't know is we don't know N, we don't know M, we don't know N, we don't know M, we don't know N, We don't know WE. And again, P bar is kind of a wild card. WE is from a model that you select. Okay? That's WE of T is a model, right? But let's talk about what you don't know. You don't know C sub F, and C sub F is equal to a function of pressure. It can be very dramatic. Okay? So can P bar, obviously. We need to know P bar. We're going to forget about this M thingy. We'll just say that there's no gas cap. So that leaves us with how many variables? Okay, well, this thing should be solvable for N. We hope. Dilhan, anything else?
Do we know PI?
We think we do, but that's a good point. Believe it or not, PI can be a very difficult variable to establish in the field. So, how many variables do we have here? Let's make a list. Our objective is N. What are our variables? Dilhan says PI. Tom says P bar, CF, and that's a P bar actually. What else? WE.
Do you know WP?
Sorry?
Do you know WP?
Yes, sorry, thank you. It's something that we know. Thank you. I forgot to mention that. What I was doing is usually when I have green color, I go through and mark all the PVT stuff in green, which is obvious, we know that. But you're right, we do know the measured rates and or volumes. So how do you feel about solving an equation where the objective variable, what the hell? The objective variable is here. And okay, we can guess probably pretty accurately or get an estimate of PI that makes sense. Hopefully we'll have an estimate of P bar that makes sense. Now here's where the difficult part is. We have no idea what CF and WE are. Why? Tell me where I can get estimates of CF. Core. And this is not just any old core analysis. This has to be special stuff. Okay? And you guys have had me for petrophysics, so you know that you have to be able to calculate pore volume compressibility, and it can change severely. What about WE? Man, me and this thing are having a great time. Okay, so WE is from a model, and you're going to spend Petty 323 talking about all the models. Fetkovich, Van Everdingen and Hurst, the Shi model, the Wang model, the Smith, the Jones model. I'm not making these up. I mean, the Smith and Jones I did, but there's a whole bunch of them. So this is impossible to solve. All right. Let's go back and do something useful. Ready, Marmina? Now what we're going to do is we're going to solve for NP over N. That's the recovery factor. We're going to have BOI over BO. We can say, whatever, that's approximately 0.95. And then we're going to put in a PI and a P bar and a CT. And when we substitute these values into this equation, what do we get? That's how much energy a liquid has to move fluid. Okay? This is fluid and rock expansion only. You get 5% recovery. How do you get the other 95 out? If this were a gas, gases are infinitely compressible. That's not true, but I mean they are highly compressible. And if we have a molecule of gas in this room and it wants to get out, it will bounce around until it finds a way to get out. But liquids won't do that. If we have this room filled to the door with liquid, the liquid's going nowhere. But if we have a molecule of gas in here and the door's open, it's eventually going to bounce around and get out. So the theoretical maximum recovery for a gas is 100%. The theoretical maximum recovery for a liquid is whatever the energy the liquid has in it. Now, there's a strange little twist of fate in here that God gave us a hand, no offense, and the way he did that was by fluid expansion, plus when you go below the bubble point, you have gas expansion. Remember that jump in compressibility? That supplies more energy. The gas phase has enormous potential to move fluid. You're going to hear people from around the world talking in the context of what the recovery efficiency for their reservoir is. What's the recovery efficiency in Turkey? You don't know because you're a real reservoir engineer. But when you go to other places, what's the recovery efficiency in Saudi Arabia? You want me to repeat the question? Okay. They say it's 70%, but you have a huge water flooding effort, at least in Gwar, to achieve that. If you go to Iran and ask them what the recovery efficiency is, they'll tell you that every reservoir recovers 70%. How do you affect your estimate of recovery? You can either be too high on your estimate of recoverable fluids, or you can be too low on your estimate of in-place fluids. That's how they get the recovery efficiency to be so high in some cases. I'm not saying anybody's cooking the books. I'm saying that there is a misunderstanding of what really the mission is here. Our mission is to recover as much as we can, but each and every reservoir, like each and every person, is going to be different. You're going to have to tune the recovery to the situation. Now, if we go out to the Clear Fork, who's from Midland? Anybody? No? Yeah? Okay. So if we go out to the Clear Fork, what's its primary recovery? It's about 8%. Okay? What's the Sprayberry's primary recovery? About 3%. These are horrible reservoirs. All of their energy is being consumed just moving a molecule of fluid to the wellbore. Okay? There's not much to work with there. So how are you going to charge up a reservoir like that? You're going to inject more, are you going to inject water into it or something like that? But if it can't travel, it's not going to do anything. The Clear Fork, what they did is they injected way over fracture pressure and just pressured the whole mess up. The recovery, the secondary recovery is probably only another 5 or 6 or 7%. But they're injecting and producing enormous volumes of water, causing a fracture system, a hydraulic fracture system, and hopefully recovering more fluid. There's also issues of fracture orientation there. But the Sprayberry, however many tens of billions of barrels it has in it, it's going to continue to have those well into the future. Now this is a gas material balance equation, and let's very quickly do the same thing. What do we know? We can estimate the Z factor, we can estimate average reservoir pressure from gas wells because we have state reports on those. We have the initial Z factor, again, initial pressure, gas produced. We know if there is any gas injected, we know that. We know the water produced and the water formation volume factor. We know BG, we know WP, we know WI, we know BW, and what about WE? We don't know WE, so we have to turn that around. What is this CE thing? What is CE? This is an unknown function, and this is an unknown function. So how do we get around this? What's pricing game rule number 0? Cheat, okay? How do we cheat? Somebody help me. Mr. Moss, gas injection? None. Water production? None. Water production? None. Water injection? None. Water influx? None. All of these go away, correct? No abnormal pressure effects. And what do we get? We get this. Okay? And how does this equation look as a plot? You already know this. It's P over Z. Of course, at average reservoir pressure. GP. And we have a nice line that forms, hopefully. Okay. And in theory, this is GP max, which is also what? It's G. How do you know it's G? Sorry? How do you know that? Looking at the equation. Make pressure equal 0, and what happens? 0 divided by X is equal to Y, right? And then 1 minus 1 over G, GP, and this, of course, is max, right? What is Y? Doesn't matter. It's PI over ZI. What is X? Doesn't matter. What's 0 divided by X, class? 0. What's 0 divided by Y, class? 0. And then what happens? We get GP max is equal to G. See how simple that was? The equation tells you that. So the theoretical recovery of a dry gas reservoir is 100%. We should have a quiz on this on Wednesday, I think. Should we have a quiz with real data? And should it be real data that might have a kink in it? I like that idea. Okay? Now, in the Dake book, the DAKE book, this equation is not written in the same form, the abnormal pressure equation. This came out of a guy by the name of Fetkovich. He wrote this equation, and what he's trying to do is explain that there's some non-net pay and there's some aquifer, and of course this is a reservoir volume, and he's trying to explain the influence of abnormal pressure from the expansion of the aquifer and the expansion of the non-net pay. We don't really need to worry about that. Why? Because we can never measure those things anyway. The Dake book it uses, I think, some sort of C hat or something, but it's fine. That term's all right. So we're going to leave the gas material balance equation for a second. We're going to leave this slide, and we're going to look at some data plots. Everybody ready? Okay. Now this is an example of abnormal pressure. If you take this line based on these pressures and you extrapolate, you get what's called the apparent gas in place. Mr. Zanero, is this good, bad, or ugly? Why? Because it ain't real. How do you know when it's real or not? Only after this thing decides to turn south, right? What happens then? Because you went to the bank and you told them, I'm going to get 375 Bs out of this. And they loaned you money to develop this reservoir for 375 Bs. And then you came back and you said, oops, it's only going to make 200 Bs. Does this happen, class? It happens every single day. The reason that people noticed this was the late 60s. They were offshore Louisiana, and they thought the pressures were awfully high and that the productivity or the reserves projection looked really good, this apparent straight line. And then after a while, things turned south. And what's happening is that over here, the reservoir is unconsolidated, let's say, and the gas itself is supporting part of the load. And then when we get over here, same reservoir, but now it acts like a normally pressured system, and the gas is just in between the pores. So over here, the abnormally pressured system, the gas is actually supporting part of the overburden, and that's what projects into this apparent straight line. Is it actually a straight line? Yes. No. Maybe. Tell me what you think. What's the letter D? It doesn't matter. Why doesn't it matter? Mr. Cottle, why doesn't it matter? Because there's not a damn thing we can do about it. Right? Okay. So then what we've done is we've created a secondary projection on this trend, and that's the way we estimate the true gas in place. Mr. Zanero, somebody saw this long before the idiots that came up with this plot, okay? If you can tell me where this magic pivot point occurs, I'll give you a hug. Okay? Okay, then I'll give Marmina a hug. If it doesn't, then I get to save this little event for later. Anybody want to help Mr. Zanero?
Gas one decides which is full volume that's consolidated, whatever that is.
Anybody else?
Water influx?
Sorry? You don't get a hug, you get something else. I know where you're trying to go. But if it equaled overburden, then the fluid would be supporting the entire load. There'd be no rock there. What do you really mean? Effective what?
The effective pressure, like the overburden minus hydrostatic.
Which is called? He gets a hug. He gets your hug. Okay, so this is the hydrostatic pressure. And of course, it isn't perfect because there's a little window here, right? Because this isn't perfect. But we should have seen this coming a mile off, right? That if you're above the hydrostatic pressure, that there's a potential for something bad to happen. So your logic would tell you that you need to start watching out for what's going on when you're in the Romulan neutral zone here. That's too far back for you guys. Okay? Keep that in mind. All right, we got a couple of seconds. Let's go to Plan B. This is Mr. Prasad's SPE 16861. This would have been approximately 1986, 1987. This is his data, his comments. I've just made a nicer graph out of it. And he saw this. Did you go to the next slide? Is that how you knew this? No. Because you didn't call it the right thing. See, if Mr. Zanero had gone to the next slide, he'd be getting a hug. Okay, so what do you think? I'm going to go off the screen here. So G apparent is real big. And then the most likely answer for G is somewhere around here. This really happens, people. What happens if you're caught reporting G apparent? Time to work on the old resume? Yeah, okay. They don't seem very interested in me. I guess they want their quiz. If I go back one, does anybody see this as a quadratic? Could it look like that? not based on,
The equation I showed.
we don't know what that CE looks like, but that's a good point. That CE is what's going to control this, that effective compressibility function, and we need to know what it looks like. You'll notice in the next slide, and then the one after it, I would, let me just leave this in their minds. I would put this in my mind for Wednesday. How's that? Is that a good way of leaving it? Okay. Dilhan's in charge now.